very much. Okay, so welcome everyone. My name is Daniel Bulanda, and I am the PhD student at the end of my journey after the research. And today I would like to present you some status update, but which is basically what my PhD thesis is about. Sorry, should I enable my microphone? Or
no, this microphone should work.
Okay, so the topic is Associative Neural Networks, development and application in two branches of medicine, specifically cardiology and allergology. So today I'm going to focus on 4 main points. The first one is for those of you who are not aware of this stuff, what is MARN, which is multi-associative neural networks. So I will introduce the topic and show some theoretical basis and applications, possible applications. Then I'm going to classify, which is some sort of abstraction over the MARN, which uses pattern neurons, to provide a classifier, and not only, what we can see later. The third part is a bit different, but connected to those two, is about pollen seasons prediction. We use data from University about pollen season for birds and grasses, and we also use MARN, among other classifiers, to predict pollen seasons. The last part is about the flex points algorithm, which is basically an ECG conversion algorithm, but we applied this algorithm to pre-process data for deep neural networks, specifically convolutional neural networks combined with LSD and cells, to see if such compression and extraction of medically valuable information can improve the overall quality of those deep neural networks. Okay, so let's switch to the first topic. I'm not going to focus much about the very general stuff, and in details it could take a day to explain everything what's here, but just very briefly to grasp the idea for those of you who are not aware of this. So I would like to start with UI-KW pyramid, because I like this approach because it gives a feeling what is our goal. Because our goal, while we are constructing MARN similar architecture, is to model somehow knowledge. And that's why I'm also often comparing MARN to knowledge graphs. Because I believe, or we believe in scientific team, that explainable and connected data is the key to better, a big word, but that's the goal, to better AI, maybe not based only on statistics, but and stochastic processes, but also on some internal representation that is that has some state which evolves over time, maybe concept-driven issue that is somehow instability. Yeah, so going back to the pyramid, as always we start with data. In the modern computers, we have plenty of data everywhere, so that's not an issue. But what is important is to represent data on the lowest level precisely and in a way that enables further information extraction. So we focus much on how to represent data in our models. Then the second part is interpretation. I like to think about this as to interpret data, we simply need an agent. So someone with something which has some position to assess the data and its usefulness to the agent itself. So usually in simple scenarios is that information is added based on the goal which is assigned to the neural system. And then association between chunks of data produces knowledge. So the scaling is the most important factor here, because we can connect, for example, features that explain a human being or a dog, and we may have 10 dogs and humans in the data as an information, because the interpreter is aware of what's dog and what's a human being. But knowledge arises, emerges, I may say, when the interconnection between various neurons representing data are richer and richer, and then we may cross the line when we can extract new unknown information. That's simply because we connected enough data in a smart manner to enable insights and wisdom is a very skyrocket word. Maybe not very useful. It's simply said that it's an application of knowledge to solve complex real-world problems. And then again, another picture represents this, but in terms of data points itself. So we may see that the more connections we have, the higher on the pyramid we are. And very quickly, on the data level, we use a concept called ASA graphs, which is basically our own idea and implementation how to handle data on the lowest level. So we developed tree-like structure, which stores neurons inside, and those neurons are connected to each other with sort of similarity connections between them. This allows us fuzzy matching, fuzzy activation, and more. So we did it because we wanted to somehow connect continuous space, which is very frequent because usually each sensor collects data which may be approximated to continuous data, but the idea of MAG itself is sort of, let's say, symbolic AI. So we need to somehow convert continuous feature space to some sort of symbols which then may be abstracted, interconnected to each other, and processed further. So that's why we had to take care of the data at the lowest level to be specialized in this topic. We also often call them sensory fields because there's somehow relation to biology, where we have sensors and neurons inside the brain, and sensors somehow get the data from the environment. So it resembles this architecture. So here we can see some other visualizations in three-dimensional space. It's a longer visualization, not feature space, of course, where you can see that each sensory neuron here is connected with another with some weight, which is a sort of similarity weight between them. And this, what is important, this enables vertical connection between data. So we are not only aware of what comprises each neuron, each object in the environment, but also what are the similarities between objects based on selected features. Because we can move vertically for each feature which describes a given role, which is basically an object. And this was published a couple of years ago, and with very decent results in terms of very simple operations, but this is very low-level structure, so it's not very complicated. Sorry for that. Yeah, anyway, maybe you need to imagine that the results of insertion, deletion, search are very good and very, competitive to other state-of-the-art data structures here. Okay, but moving further, I said that I like to think about one as a knowledge graph because it models knowledge, so why not? It is a graph. It models knowledge, so why not just assign this label to it? It is a sort of knowledge graph, and I like to call it associative knowledge graph, for the sake of naming. But in the industry, there are two other very popular types of knowledge graphs. To be honest, if one wants to explore the topic, usually can meet a lot of companies and a lot of frameworks, open source or commercial, that are based on two types of knowledge graphs. So, pretty knowledge graphs, they're basically completely flexible and free architecture that you have plots, you have edges between them, and you can assign any type of property to node, to edge, and basically that's it. That's the only constraint we have. Extremely flexible structure, but sometimes it is required to have such flexibility. That's why it exists and it works. The other very popular approach is something which is called RDF, so Research Description Framework. It's a standard made by W3 organization, so it's a bit different category, but behind this thing we have some idea which are very popular. So we have something which is called triplets. Something like subject, predicate, object, or maybe more common words, noun, verb, another noun. Some object is acting on another object. So basically we can say that John, which is subject, is a friend, predicate, of Susan, for example, and Susan is an object. So we may have another entity which is object, but object may be also just a simple property like number. For example, there is John, age 55. Something like this. And what I'm saying, this is just to maybe somehow find a spot where associative knowledge graphs are. And this is the most strict structure of them, because we only allow for very specific types of connections. We call them defining connection, inhibitory connections are like this. But the key part is that all of the structures are knowledge graphs, but in case of math, we allow only for very specific types of connection which have some semantic meaning, and it enables us to construct algorithms that may use this assumption what these connections are, so we don't have to somehow figure out what's the semantic meaning of the verb friend. Who knows? Only people know. Computers doesn't know it. So that's a very important part that we allow only for specific types of connections. And we can construct algorithms on top of that. So some visualization. This is a picture which presents how it may look like in an abstract way. So we have sensory fields which are composed of ASA graphs. And here we have sensory neurons, which represent some real-world values. For example, A may be age, and A1 8 years old, 8 to 3 years old, stuff like this. Then we have object neurons, which are basically rows in table, for example. So they represent some objects, and objects have features. That's why they are connected.
It's invisible.
Right?
And change maybe.
What characteristics?
Projector, maybe, or
What's the difference?
Yeah, I'm not sure that this can be improved much with this.
the setting goes better.
Brightness down.
Right. Let's,
Just up. Label, of course.
Oh, now it's
Okay. The object may represent the rows in the table, and so objects here, and the cluster neurons may be columns of features in this very simple architecture. And as I said, we have various types of connections. The most important one is defining. So we can see that, for example, O1 is defined by A1, but also for example, O2 may be defined by O3. So we can easily imagine that there may exist some sort of hierarchy between. Okay, we have also other types of connections. Explanatory connections are just the opposite of defining connections, but it is important to distinguish them because the algorithms are different behind the scenes. We have also similarity connections, which you met when I spoke about ASA graphs. Sequential connections are really important when we use ICS data, or maybe not exactly. Maybe we need to represent sequence, logical sequence, not necessarily time sequence, but for example, like an order, so like this. And inhibitory connections are also very interesting topic, but they are not well used yet here. Okay. There are many variants of those networks, like passive or active. So they may be some dynamic systems that adapt to the continuously changing environment in a bit of uncontrolled manner, or they may be passive. So once we fed the data once to the model, and that's it. And the model now serves the other purposes, like inference, for example. Yeah. But what is important, this is knowledge graphs, but at the same time, this is a neural network. So we have each node is a neuron, which has its internal state. It may have some activation function. It aggregates signals from other neurons. Yeah. So we combine the idea of knowledge graph and neural network. It's a very popular topic nowadays. Just how it may be constructed from tables. I think I can skip it. Not very important. Maybe two important things. Those models doesn't require any sort of encoding, like one continuous or entropy encoding and imputing features. Why that? Because we completely get rid of the idea of tables or tensors, languages, whatever. So we don't need to feel an assumption that everything must be a number, because this is a symbolic structure. So symbol doesn't have to be a number, it can be anything. That's why we don't have to impute values, because if a given value doesn't exist, for example, because that data is broken, or just doesn't exist because it doesn't describe something, then we simply don't connect the dots, and that's it. We don't have to impute values to fulfill the requirements of large tensors and stuff like this. And we have also developed a prioritization algorithm, which basically learns what are the priorities of neurons inside the network, which is a very interesting topic. Maybe I won't cover it yet, but just to give you a grasp that we may also train those neurons based on different kinds of goals, targets for them, so that one may be more important than another, so bigger in terms of biology. Because that's how it works in living organisms. If the neuron is more important, then it may be bigger than other neurons, so that it can produce more energy and bypass the potential to further and more. Okay, this screen shows how it behaves in terms of some queries, but this is very normal. Very standard benchmark for any type of knowledge graph. It's not a specific ability of Magn. Any kind of knowledge graph will be significantly faster for some type of queries compared to relational databases like Postgres or MariaDB. We also developed a similarity vote classifier, which was used in the next topic. On signal prediction, this classifier is basically similar to K-Newell's algorithm, but very different at the same time. Because in a short, we activate the features, for example, coming from training from testing example, and the activations are classified as I showed previously, and neuron objects, the object neurons itself, and then the neurons are activated. They may also pass it further, but they are somehow activated, and we can then count the activations, create some sort of ranking list, and we may allow some of them to vote, and they may take that, okay, maybe this is the best class which represents the testing example. And this result represents some benchmarks. For some applications, the reliability is very good. For some, it's not. As always, nothing is perfect, nothing is too generic to be true. But what is important is that those algorithms are extremely fast because they belong to family of algorithms called lazy algorithms. So no training phase itself, and the inference is only just asking the graph what are the connections and what are the activations. So it's extremely fast in training and in operation. That's why the first place belongs to. And we have another factor is that implementation low-level programming languages. That's also important here. Okay, and we published 2 papers based on that. This one is the most important one, which describes the basic principles on the conference, and this one is about the application. Okay, and there is at least one application used. It will be open source again, because for a while it wasn't, but it will be open source, so anyone can use it, which is basically an implementation of all those ideas, and you can load any data and test it on your own. Okay, maybe a bit more complex topic, because the topics presented was maybe a bit too long, but introduction to what is new in the past year. So in the past year, we have developed an algorithm which is called Associative Neural Classifier, and we introduced 2 new types of neurons to the network. which are range neurons and pattern neurons. So range neurons are sort of connect sensory neurons, which are somehow too similar to be separate neurons. Yeah, so some sort of clustering maybe around the feature space. And we have, the idea is a bit complex in terms of implementation and maybe algorithms behind the scenes, but this is not very, this is the, I would say, smart algorithm, which utilizes similar connections and also it's aware of other connections. So we have, for example, WITS algorithm, or Associative Neural Information algorithm, that somehow assess the value which is assigned to symbols. So we can eliminate some of them, merge them maybe, or I don't know, switch range neuron to other neurons. So those algorithms somehow provides better, more informative range neurons. And then instead of connecting sensory neurons to patterns, we use range neurons to connect to provide pattern neurons. So pattern neurons is some sort of abstraction over data. So if we may think of O2, so the object neuron as something that represents a real life object, then pattern neurons are not directly connected to some living entity living in a data, of course. They are abstractions of the data. So they connect features, ranges, maybe something else also to some abstractions, to some entities that represents combinations of features or combinations of features and other patterns. That's why, again, we can produce a hierarchy based on that. And those patterns then explain the objects. So imagine that this potentially will be a very powerful framework, because patterns are that's about how the human brain works. At least that's my belief, but not only mine. There are many publications, many books that argue this, that patterns are the most essential entity that describes how the human brain works. Patterns and associations between. That's why we are following that chart and trying to model this stuff in our networks. Yeah, so those algorithms represent how to construct the pattern neurons and range neurons from sensory neurons and object neurons. But maybe I will skip the details and just go further to this topic, which explains how we assess the patterns, because we use various measures to state if a pattern is useful or not for a given task. Because in general, every pattern may be useful. So we use metrics like SAFOR, which states how often a given pattern occurs in the data. We also use confidence and some other metrics, like for example, least. But confidence is basically how a given pattern is uniform. So if it states something, how sure can we be that this pattern is true based on data, of course? No random values here, no stochastic processes, everything is fully explainable and deterministic here. And based off that, for a given task, because this is a classifier, so we classify things, so we need to assign classes to test examples. So for the sake of classifier, we use those rules and we divide them into three main categories. First class rules. So those rules are just confident enough to be sure that if a given rule exists, then our classifier can't do any better. So we just assign a class which is represented by the rule. The other type of rule are harmful rules. So we know that those rules have very low confidence score. So we should exclude them because they there is no information assigned to them. So the entropy is pretty bad, and we should not use them in any case. And the third category is spare rules. Spare rules are something in between. So we see that they bring some information to the table, but at the same page, they are not so confident about them. So if we don't have any first-class rule for our newly coming training example, then we can ask the spare rules storage if maybe there is something to help us with this issue. Yeah, that's how it works. And here we can see the results of this classifier. This is a very good classifier, to be honest. We compared it to probably the most popular classifier out there. So data scientists and machine learning engineers usually use XGBoost, random forest, or some sort of simpler classifiers like logistic regression. And of course, neural networks are very popular nowadays. And we compared to them. And it seems that for data sets which have a high class imbalance and a lot of rare patterns inside, this classifier is very, very good. Achieves a performance which is comparable to other state-of-the-art models, because those results doesn't necessarily state that our classifier is the best. It states that this classifier is on par with other state-of-the-art classifiers. That's okay, and this one is still not published, and fun part is that we sent it to a knowledge-based system, very good journal, which is 200 points, Polish points, and they assigned one review to us, which is quite positive, and another one was about completely different paper. We didn't know what to do with this. We are somehow figuring out how to deal with it. That's a very, very interesting history about how to publish it. Okay, maybe let's switch the first topic, which is coincidence prediction. Maybe more interesting to some of you because now we shift from the abstract domain to the practical application domain. So I guess that for some of you it will be much more interesting. So we have a cooperation with Jagiellonian University, and they shared their data, which is not public, so nice that they did it, about ponency zones in Kraków during the last 34 years. So pretty long time, and we focused on two types of pollen, so birch, Latin betula, and grasses, poaceae. Biologists often use Latin instead of English. So that's why it's good to know it. Okay, so the station is located on the Kolegium Śniadeckiego in the center of Kraków, about 20 meters above the ground, and magic method maybe not very important here. And this figure is really interesting because it shows how the concentration of pollen distributed in terms of day of year among all the data, so this is 34 years. This is very interesting, especially for people who maybe suffer from allergy. A small anecdote, I used to live in Kraków, and 5 years ago I moved to a small village, Polechowice. Probably some of you know this, because it's near the airport, Biocybernetyki airport. And I've never suffered from allergy, and just 1 year after this move, I had a huge 4th class allergy to birch. So the first one. And I can confirm that this plot is very correct. So yeah, it just works. And fortunately, we're now. So but you can see that those distributions are completely different. So we decided to use different models for the tolerance, different for pulses, because here we can see a huge spike, maybe this better, a huge one spike, and these plots for grasses are much more irregular. Okay, in addition to pollen concentration data, we also use data from Balice meteorological station, about 10 meteorological factors: temperature, humidity, cloud cover, sunshine duration, speed, sea level pressure, radiation, and snow depth. We use them because it's maybe obvious, but it needs to be included in the modeling because they highly influence how those trees, grasses, reject the pollen. Okay, so maybe the main issue here is that this meteor station is 11 kilometers distance between the pollen station and the station. So that's a small issue. We somehow elaborated on it, and without that it's not very relevant, but it may be relevant for the model. But we simply didn't have any other data for that. Okay, and we used many models in this topic. So some of them were able to use time series data like convolutional neural networks or LSTMs, but others require some sort of feature engineering. So for that purpose, we used exponential moving average, which is a very, very good measure to move from unstructured time series data to structured data when we have features that precisely describe those uneven and unstructured data. So we used exponential moving average for different windows, like 3, 7, 20 days, and some sort of relations between them are also modeled. And the target variable was converted to categorical space because we wanted to provide a classifier. This is relevant from the medical point of view because those 3 labels are important for the doctors to apply appropriate medications based on this, because they have their own algorithm and they use different steps if the concentration is high or low based on this. Okay, so the modeling part was as follows. We used the models from 4 families. I said you previously about Mark and that this is a lazy classifier, so basically. And the similar one is here is k-nearest neighbors, also used here. We use linear regression from linear family, and this is the only one model which assumes number distribution of data and some other assumptions. So this one is only parametric model, other are not. Tree-based models, so decided to use 3 here because it's very happy in terms of such applications. So we use decision trees, random forest, and XGBoost. And for deep neural networks, we use the combined architecture, which is convolutional neural network here with max pooling layers to denoise the data and reduce the dimensionality of data, because that's what max pooling does. And convolutions also somehow distract the noise and try to figure out what are the most important features. This is in one-dimensional convolution, of course, but it works. Then those features, so compressed and denoised, are passed to the LSTM or automated recurrent unit cells to model temporal dependencies between those features. This is a very popular architecture, and it works really, really well in many scenarios, not only point prediction, but I can assure you that it works, for example, in the financial data. For example, I do something in crypto market, and this is a real business, and it works. Yeah, so using convolution actually plus some sort of temporal modeling. For example, let's see, maybe attention, maybe something else. Yeah, it works really, really well. Okay, and here the results. There are some maybe one remark. We used 3 types of targets. So we predicted 1 day ahead, 4 days ahead, and 7 days ahead. And for different types of modeling, we achieved different results. And for example, for longer periods, usually deep neural networks was the best. But in general, I may say that XGBoost was the best one among them. And Mag was also nearly the same, but a bit worse. But if we take into account execution time, memory consumption, and stuff like this, then Mag is a clear winner with no other competitor, which can be, with similar performance here. So in general, I may assume that I may say that those experiments proved that Mag was a very useful classifier and used, especially in scenarios where explainability is important, where resources are constrained, so we can't use heavy networks that rely on huge computational power. Okay, those plots represents prediction and your data. So you can see that it works, that probably we also analyzed features in terms of feature development, and we used the output from XGBoost because it's under kind of set features. So we also use associative neural information from the Mag, which also basically does the same. So says you what's the correlation. Is not proper word, the correlation is something else, but let's say correlation between maybe common information between the target variable, so the 3 classes of the pollen concentration, and the other biological features like the actual for instance. We also used association rules and this type of plot to present that there exists some combination, because the association rules is some combination of features which produces pattern. And so this plot represents that there exists some combination of plots of association rules that highly influence the predicted category. The bigger the dot, the more popular they are, and the higher on the plot, the higher the lift is. So the lift says that pattern is clear. Then we may assume with very high probability that no other category can be assigned to this. So basically, it states how pure the rule is and how confident we may be by using it. This is the summary again. If it is graphical abstract, may just give you a better idea how it works. So data, modeling, pollen prediction, and classical characteristics. Okay, and very quickly, and this paper was accepted not fully accepted because we are in the major revision process, but everything goes well in flows one, the first one through. And the last one is the flex point algorithm, which is ECG signal compression algorithm. What is new in the previous year is that we applied this algorithm to somehow improve the performance of deep neural networks. Yeah, so in short, this algorithm uses a dedicated filtering algorithm, which is based on linear and quadratic approximations. Then it finds derivatives up to fourth derivative of the signal, and we use third and fourth derivative to find zeros. And that's why it's called flex points. Because zeros in the derivative say that they make some sort of flexment in the shape of the curve. And then we use a bit sophisticated algorithm to filter those points, because not all of them are so impressive. And the last part may be to use polynomial approximation, but we didn't use it in the experiments, but just because it didn't work well. So here you can see how it works. So on this plot you can see how the noise algorithm works. So pretty well removes the noise, and then after application of the flex point algorithm, you can see the characteristic points here. We may somehow be sure that no relevant medical information is compressed, and that's what the could go. There is also an application which can be used, an open source application and available online to check the flex points in action. One application on predefined data from MATBAH arithmetic data set, and the other one can be used for any type of data. And this algorithm was published in Journal of Electrocardiology this year. But on top of that, we use MITBAH arithmetic data set to, as I said, to deep neural networks to check if application of the flex point algorithm as a preprocessing step can improve the performance of them. And this is the characteristic of this data set, but probably if one is aware with ECG processing, you know, because this is the most popular one there. Okay, so the architecture used is as follows. We used three convolutional layers followed by max pooling layers to reduce the dimensionality and also to the noisy signal. Then there are two variants. One uses LSTM cells with 20% dropout, and then two dense layers also with dropout, and softmax at the end to produce classes, of course. But the other variant is just to bypass directly to dense layers, so skipping the LSTM cells, just to provide some variation here. Okay, and the results are quite promising. The table here shows that behavior of the flex point algorithm compared to Raman-Douglas Picker algorithm, which may be treated as a competitor to the flex point algorithm. So we can see that compression factor is significantly higher, which means that it's unexplainable. So the flex point algorithm compressed better, but it produced worse error term than Raman-Douglas Picker algorithms. So it may one may think that it's not good, but we need to be aware that those are qualitative measures. So they only assess the deviation from the raw signal itself, nothing more. Squared, of course, but never mind. So what is the goal of the reflection therapy is to extract genetically valuable information. So we expect the error to be higher because we know that there is some noise which needs to be rejected somehow. Yeah, that's how it works. So we are totally fine with higher PRD scores, and the overall quality score is very similar to those. And the final results here are as follows. So the experiments proved that for the neural networks with convolutional and LSTM cells, the flex-point algorithm improved, in any case, the overall accuracy and difference score, with some deviations. For example, in some cases, maybe the recall or specificity was better for LTP, but in general, it significantly, the flex-point algorithm significantly improved the overall performance. For convolutional layers only, the situation wasn't so good, but still good. So in most of the cases, the flex-point algorithm provided improvement versus raw signal and versus the Raman Douglas Picker algorithm. And this paper was sent to IGCNN conference in Rome this year and was accepted. Yeah, so basically I think that's it. We covered our 4 topics. I hope it was boring for you, and I'm looking for your questions.
Then for your interesting sorry not to be but to ask audience. So in this lecture, I'm doing the remote connection. One question.
Start
From the remote, but who is that?
Nico.
Please.
Thank you. Can you hear me? Am I audible? Okay. Thank you for your presentation. It was very informative. If you can rewind to the slide about association rules classifier, or I can just ask the question if okay.
Which one exactly?
It was titled Association Rules Class. Yes, that one. Yes. Yeah, this one. Exactly. So we have specializing here and generalizing about the criteria. So I was wondering how these are weighted in the ranking process, because if we're talking about the context of the data that where patterns may vary really widely in specificity. So I was wondering how this specializing and generalizing would work in the ranking process.
Okay, that's a very good question. Sorry that I didn't explain it well because I wanted to be hurried and I skipped it. But this entire point works as follows. The algorithm first assess the confidence of a given rule. So if the confidence is the best, then simply this first class rule is picked. But if there are more than one rule that have the same confidence, which is really common, maybe it's not obvious that it is, because we produce billions rules very often. So many of them may have the same confidence score. So if the confidence is the same, then we ask for support. So support is basically how popular, how common the rule is. And if the support is again the same, which is also a very common scenario, it may be not intuitive, but that's how it works, then we ask for rule length. And rule length, we have 2 cases, and this can be treated as a parameter of the model. So we need to decide a priori which would like to have a generalizing model or specializing model. If the model is specializing, then we pick the longest rule possible. So specialization, we look for a rule that describes the testing incoming example in the most detailed way. That's why we call it specializing rule. On the other hand, if we decide to use generalizing rules, then we look for the shortest rule. Because maybe for our application, we don't want to focus on those details and we want to extract the most generic knowledge. And in the experiments, we proved that specializing rules are better in like 90% scenarios, but for this 10%, generalizing rules works better. So that's how it works. It's a parameter of the model which can be specific.
Thank you very much. So it's based on the assumptions or the basis that we determined before, like starting the experiment. We just, it's based on the human expert, like what they want exactly and what they want ranked.
The general, way default parameter is specializing rule. But once you know that you need to extract only the most generic, features from the pattern, then you can go to the generalizing part. But in 99% of cases, I would just use specializing rule because statistically it performs better. Yeah, that's how it goes. It's a very detailed parameter and very technical one. So the end user may not be interested in it at all. But I'm presenting it how it works behind the scenes. So for advanced technical users, they may then decide which one to use, but otherwise the specializing one is the best one.
Thank you very much. May I ask the second question? Do I have time?
Of course.
Yes, please go on.
Thank you very much. So in another slide, I'm not sure which one it was, but you were talking about imputation for the missing associations.
Yes, of course.
And you mentioned that because the association simply, yes, exactly. The association doesn't exist, so we don't have to impute. You don't have to impute the missing data because we just don't put it there. But isn't that equivalent to dropping like the rows or the columns with the missing data for, let's say that the data doesn't exist? Mm-hmm.
Absolutely not. Because you can have a column which has 90% missing values. And dropping the entire column is a huge miss of data. And at the same time, you can have a row which, let's assume that you have 20 features and only 90 are with some real values and one is missing. Then dropping the entire row is also harmful because we lost the information about the entire record. Just because this one crucial feature is missing. And maybe the information that this feature is missing is also informative, because maybe for this type of object, this feature simply doesn't make any sense because of maybe poorly designed data set. It happens all the time. Most of the data are of poor quality. So if you design a table and there are many missing features, still the data you have, and you have to figure out what to do with it. So you can impute the data based on mode, media, or stuff like this. But this is again, somehow artificial data, not real data, because you are imputing the median. So this median that doesn't exist it's not true that we assign median to a given row. So any sort of these techniques which are enumerated in the point one, all of them are not, very. Sorry, maybe not all of them, but some of them, especially imputers, are not very good in terms of the accuracy and not always proper in them. But for statistical models like deep neural network, of course, it works.
Thank you very much for the points. I'm not sure that I follow, because I didn't mean about I didn't mean the imputation itself. What I meant was when you said that when the association doesn't exist, we simply don't put it there, so it wouldn't be in the associations, right? So before we impute the missing data, what we do is, for example, set a threshold sometimes to say that if like 50% or 40% of data in a row is missing, we just simply drop it. So I'm saying that if the association doesn't exist and we don't put it there, we don't count for it, so it means that we're kind of like, it would be equivalent to dropping a row with like maybe about 40% missing data. I'm not sure if I'm making myself clear.
Probably yes, but I don't know how to answer this because if there exists some threshold like 30% or stuff like this, then there's another parameter to the model which needs to be set, and who decides how many percent should it be to drop a row, for example. So, and Mac works in a completely opposite way. It doesn't assume any schema of data at all. It just, if there is some association between feature and row, then it is produced in the graph itself and exists, and features are associated. If there is a missing data on one column, it can be any column, then the association does not exist in the graph. And that's everything that I wanted to say in this slide. Because if you use, for example, neural network, then you need to provide a table or matrix that is fully filled with numbers. So missing numbers are not allowed. And you have to figure out with this. So you include data or you remove rows and columns. But in terms of math, you don't have to do it because the algorithms are completely different. They only use associations that exist in data. So the problem of threshold, of dropping, of imputing, of encoding simply doesn't exist because the algorithms are predefined work on the graph structure itself. That's what I wanted to say. Sorry for not being clear, maybe.
Thank you very much. I understand it now.